Hello everyone. We have been using the graph of one of the regression assumption is that the residuals are independent of the fitted values, and we also use the graph of residuals versus fitted values, right? So we have fitted values on x-axis and residuals on y-axis, and we try to check whether the graph is random. Okay, that is one of our assumptions. So today we will theoretically prove why fitted values should be independent of the residuals. Okay. So what we know is our fitted values y hat are basically linear functions of y. So we write it as hy, and residuals are also linear functions, but they are I minus h into y. Correct? Where h is my hat matrix. We know h is x into x prime x whole inverse x prime. Okay, this is my h. So we will try to see if we can prove that these are independent of each other. Our regression assumption states that the distribution of y is normal, okay, multivariate normal. So we know y is n-variate normal, okay, because y1, y2, yn, I have n components with mean x beta and variance covariance matrix sigma square into I. So we know that distribution of y is multivariate normal with mean x beta and variance sigma square I. Okay, and we also know property of multivariate normal, that linear functions of multivariate normal vectors are also multivariate normal. So that tells me that distribution of y hat will also be normal, and not just that, distribution of E will also be normal. In fact, if I consider joint vector, that is y hat and then E, so my total vector is of length 2n cross 1, then I could write this as h here and then I minus h here and then y. Correct? What is the order of my H matrix? X is n cross p, x prime x inverse is p cross p, and x prime is p cross n. So H is n cross n. So this is n cross n. This is also n cross n. So overall the total matrix is of order 2n cross n. Y is of n cross 1, and hence I get correct vector of order 2n cross 1. Okay. So what we have done is we have written the joint vector y hat and E as a linear function of y, which we know is multivariate normal. So we will now use the property. What property? That the linear function of multivariate normal is also multivariate normal. So y hat and E, this will have normal distribution with dimension 2n, expectation whatever we derive, and variance also whatever we derive. So let me write it mu of this joint vector. So I'll call it mu j, and I will call that joint variance covariance matrix as sigma j. Okay, let me now derive what are the formulae for mu j and sigma j. So what is mu j? Mu j will be expectation of h, and we have I minus h here into y. Okay, we know that h contains only x terms, and we are considering x is not as random. Since h contains only the terms involving x, okay, what we have is h and I minus h can be outside the expectations, and I'll have to worry about only expectation of y, which we know is x beta. Okay, so let me write, this is x beta. What do I get? This means I get h x beta and I minus h x beta. Okay, h x beta and I minus h x beta. Now, what is h x beta? If I try to simplify, h x beta will be x prime x whole inverse x prime, that is my h, then x and beta. So x prime x whole inverse and x prime x gets cancelled. So I'll be left with simply x beta, which actually proves that expectation of y hat is same as expectation of, y. So these are unbiased estimates. And let me talk about the second term. So the second term is I minus h into beta. So what will I get? Expectation of, I have to consider now the second term. The second term is expectation of I minus h into x beta. We just now showed that hx beta becomes x beta and ix beta will also become x beta. So this is 0. Okay. Hence, my mu j is a vector with this first component of the partition as x beta and then 0 as the second part. But our main interest is in the variance covariance matrix because we are interested in examining whether the residuals are independent of the fitted values. So sigma j we know would be the vector, the matrix that is h I minus h, okay, this into variance covariance of y into partition of this, transpose of this, that is h prime I minus h whole prime. Okay, variance covariance matrix of y we know is sigma square into I. Variance of y is sigma square I, so I will have sigma square here and then I have to multiply these matrices. What we know is H is a symmetric idempotent matrix, so H prime becomes H and H, the product also becomes H. So I have H here, then I have H into I minus H here, correct, because I minus H will also be symmetric and idempotent. Then I will have again I minus H into H here and I minus H here. So if I now focus at the off diagonal part of this, then I will have H into I minus H into H, and we know HH is H and HI is also H. So basically I get sigma square H 0 0 and I minus H. Okay, hence we have proved that the off diagonal entries are 0 0. Thus we have established that the two components of the J vector, that is the residuals and the fitted values, their variance covariance matrix is 0 matrix. And we know property of multivariate normal distribution, that if variance covariance matrix is a 0, if the covariance matrix is a 0 matrix, then those two vectors are independent. Hence, using that property of multivariate normal and the fact that this is a 0 matrix, we have established that the residuals and the fitted values are independent of each other. Is it okay? Let me stop here. Thank you.